Linear momentum. Momentum or the linear momentum is defined as mass times the velocity. Since the velocity is a vector, momentum is a vector as well. The units of momentum are kilograms times meters per second. Impulse, G. Impulse is defined as the average force times delta t. The units of impulse are kilograms times meters per second. Since the average force is a vector, impulse is a vector as well. So what's important here is we can relate the impulse to the change in momentum. Impulse equals to change in momentum. So this relationship is called the impulse momentum theorem. Since impulse is force times delta t, then the force times delta t equals to delta p. So the force is equal to, or the average force equals to delta p over delta t. So we can say the average force is rate of change of momentum. But if we expand delta p, we can write delta p equals mv final minus mv initial, assuming that mass is constant. So force becomes mass times v final minus v initial over delta t. But you also know that v final minus v initial over delta t is the acceleration. So this is, in other words, same as Newton's second law. Now let's go over an example. A tennis ball moving horizontally at 16 meters per second hits a wall. The ball bounces off the wall at 14 meters per second. During the collision, the ball stays in contact with the wall for 0.05 seconds. Mass of the ball is 0.5 kilograms. Find the impulse and the average force exerted on the wall. So this diagram shows the ball coming in at 16 meters per second, and then it bounces off at 14 meters per second. And the ball is in contact with the wall for 0.05 seconds. So these are the known values. V0, initial velocity 16 meters per second. Final velocity, negative 14 meters per second. There is a negative sign here because the final velocity is in the opposite direction. Mass is 0.5 kilograms, delta t 0.05 seconds. So the formula for the impulse is delta p, which is mass times v final minus v initial. So 0.5 times negative 14 minus 16. So that's 0.5 times negative 30. So it's negative 15 meters per second. Now we applied the impulse momentum theorem to the ball. This means this is the impulse on the ball. So the impulse on the wall is in the opposite direction but must have the same magnitude. So impulse on the wall is plus 15 kilograms times meters per second. From that we can find the average force, because average force is impulse divided by delta t. So that's 15 over 0.05. That's 300 newtons. Now consider a situation when the average force is 0 or the net force is 0. When the net force is 0, it means this delta p over delta t is 0. That means no change in the momentum, or momentum is constant. So we can say that if there are no external forces, momentum is conserved. This is called the conservation of momentum. As an equation, we can write P final equals to P initial. So now let's go over an example. A 100-gram firecracker explodes into two pieces of mass 60 grams and 40 grams. The 40-gram piece flies to the right at 24 meters per second. Find the velocity of the other piece. Assume that the firecracker was initially at rest. The initial mass of the firecracker is 100 grams. The initial velocity of the firecracker is 0 meters per second. Mass of the first piece is 60 grams. Mass of the second piece is 40 grams. V1, which is the final velocity of the first piece, is unknown. V2, the final velocity of the second piece, is 24 meters per second. Since there is no external force on the firecracker, we can assume that momentum is conserved. So we can write the initial momentum equals to final momentum. The initial momentum is the momentum of the firecracker before the explosion, m0 v0, equals to the sum of the momenta of the two pieces, m1 v1 plus m2 v2. Since v0 equals to 0, initial momentum is 0. So 0 equals to 60 times v1 plus 40 times 24. That gives us 60 v1 equals to negative 40 times 24. So v1 equals to negative 16 meters per second. The negative sign means that the first piece moves to the opposite direction to the motion of the second piece. So we can say the first piece is moving at 16 meters per second to the left. So explosions are good examples for conservation of momentum. Also, collisions are good examples for conservation of momentum. In general, all collisions conserve momentum. Some collisions conserve both momentum and mechanical energy. Those collisions are called elastic collisions. When the objects stick together after the collision, we call those collisions completely inelastic or totally inelastic collisions. So this is an example for a totally inelastic collision. A freight car of mass 5,000 kilograms is traveling at 8 meters per second. Another freight car of mass 8,000 kilograms is traveling at 6 meters per second to the opposite direction on the same rail track. During the collision, the cars couple together and travel at the same velocity. Find the velocity of the cars just after the collision and the energy loss during the collision. So since the cars couple together after the collision, this is a totally inelastic collision. And when we say energy loss in collisions, what we generally mean here is the kinetic energy loss during the collision. Now we have a 5,000 kilogram car which is moving at 8 meters per second. Then we have this 8,000 kilogram car moving at 6 meters per second to the opposite direction. So there is no external forces. Assuming that there are no external forces, we can consider that initial momentum equals to final momentum. So m1 v1 plus m2 v2 equals to m1 plus m2 times vf, because after the collision they couple together, so the total mass is m1 plus m2 and the final velocity of the system is vf. So by substituting the values, we get 5,000 times 8 plus 8,000 times minus 6. This minus 6 represents that the velocity of the second car is in the opposite direction, equals to 13,000 times vf. So we get 8,000 equals to 13,000 times vf. So vf equals to negative 0.62 meters per second. So the final velocity is in the negative direction or to the left after the collision. The two cars will be traveling at 0.62 meters per second to the left. Now to find the energy loss, we can use this equation. Change in energy is equal to E final minus E initial. E final is 1/2 times m1 plus m2 times V final squared, and E initial is the energy of the two cars, which is 1/2 m1 v1 squared minus 1/2 m2 v2 squared. 1/2 times 13,000 times negative 0.62 squared minus 1/2 times 5,000 times 8 squared minus 1/2 times 8,000 times 6 squared. So that becomes 2498.6 minus 160,000 minus 144,000. It's approximately 301.5 kilojoules. So this means approximately 99% of the energy is lost during the collision. So this is a typical completely inelastic collision. In these collisions, the energy loss is very high. This is an example for an elastic collision. Two objects A and B collide elastically. Initially, B is at rest and A is moving toward B at 12 meters per second. Find the velocities of A and B after the collision. So this is the situation before the collision. A is moving toward B at 12 meters per second and B is at rest. And after, let's assume that A is moving at VF1 and B is moving at VF2. So the formulas to find the final velocities are these. VF1 equals to m1 minus m2 over m1 plus m2 times V01. VF2 equals to 2m1 over m1 plus m2 times V01. So m1 equals to 2 kilograms, m2 equals to 0.5, and V01 is 12 meters per second. So VF1 equals to 2 minus 0.5 divided by 2.5, that's because 2 plus 0.5, 2.5 times 12 equals to 7.2 meters per second. And VF2 equals to 2 times 2 divided by 2.5 times 12, so that's 8.64 meters per second. The last topic is center of mass. So in this section we are discussing only the center of mass of a discrete mass distribution. For a discrete mass distribution, let's assume that the center of mass is given by this RCM. The coordinates of the center of mass are XCM and YCM. So RCM equals to XCM and YCM. These XCM and YCM are given by XCM equals to sum of MIXI divided by sum of MI, and YCM equals to sum or sigma MIYI divided by sigma MY. So now let's go over an example. So we have three masses located at three different positions. Mass M1 is at the origin of the coordinate system. Mass M2 at 5, 0, and M3 is at 0, 3. So these are the coordinates of the positions of each mass, and we need to find the center of mass of this system. M1 is 2 kilograms, M2 is 3 kilograms, and M3 is 5 kilograms. Now using our equations, XCM is given by M1x1 plus M2x2 plus M3x3 divided by M1 plus M2 plus M3. So x1, x2, x3 are the x coordinates of their positions, but x1 and x3 are zeros, so only non-zero value is x2. So we get 3 times 5 divided by the total mass, that's 3 plus 2 plus 5, that's 10. So it's 1.5 meters. That's the x coordinate of the center of mass. To find the y coordinate, we can write the equation for YCM, which is m1y1 plus m2y2 plus m3y3 divided by m1 plus m2 plus m3. The only non-zero y coordinate is y3. So we have 5 times 3 divided by 10. That's also 1.5. So the center of mass is given by 1.5, 1.5.